Every Huawei Ascend 910C board produced in Shenzhen shares the same quiet dependency. A column of memory dies, each one thinned to roughly 50 microns, bonded directly against the compute die through thousands of microscopic connections across an interposer, without which the accelerator cannot move data fast enough to function. That column comes from 3 companies. 2 of them are in South Korea. 1 is in Idaho. None are in China. The question this map is going to answer is not whether China can design an artificial intelligence accelerator. It already can. The question is whether it can feed one, whether it can source the high bandwidth memory that turns a compute die into a working accelerator without routing that request through Seoul or Boise. This dependency graph has a shape most coverage has missed. A sanction targets the node it can see. The node that actually governs whether the network functions is usually one position back from the visible one, hiding inside the packaging, the substrate, the memory stack bonded against the die. This map traces the line from an accelerator board back through the nodes no one was watching and marks which ones still have no bypass. The physical object this map follows is a single high-bandwidth memory stack. 8 dynamic random access memory dies thinned to roughly 50 microns each, with through-silicon vias drilled vertically through all of them. The whole column bonded to a logic die via thousands of micro bumps across an interposer. It is not the chip that gets the headline. It is the component that makes the chip functional. Consider what high bandwidth memory actually does. A large language model inference run does not bottleneck on arithmetic. It bottlenecks on how fast the accelerator can read weights from memory and push them through the compute units. The bandwidth requirement for that operation at scale is not something commodity dynamic. Random access memory on a conventional bus can satisfy. Standard memory connected to a processor over a conventional bus is like water arriving at a building through a shared city main. The pressure is real, but the pipe is shared with every other building on the block, and the main runs meters away beneath the street. High bandwidth memory is a private riser drilled directly through the floor. The bandwidth is dedicated. The latency drops because the distance shrinks to millimeters, and the entire building's plumbing was designed around that riser being present from the foundation. You cannot retrofit the riser after the building is finished. The accelerator architecture assumes the memory is inches away, not meters away on a printed circuit board. That is why the Ascend 910C, like the Nvidia H100 it competes with, is not designed to work with standard memory. The board assumes the stack is there. Remove it and you do not get a slower accelerator. You get a compute die with nowhere to put its data. SK Hynix is publicly identified as the primary high-bandwidth memory supplier to Nvidia's H-series accelerators. Samsung and Micron supply high-bandwidth memory to other vendors. Reports from analysts suggest SK Hynix held a leading position in the most advanced high-bandwidth memory generations heading into mid-2025, though precise market share figures vary across sources and should be treated as estimates rather than settled fact. What is not an estimate is this: no Chinese supplier is in confirmed commercial high-bandwidth memory production at the bandwidth specifications that current artificial intelligence workloads require. The United States Commerce Department publicly extended export controls beyond the compute die to cover high-bandwidth memory above certain bandwidth thresholds, per documentation in the public record. My read on this: the export controls were accurate, but the dependency map behind them was one node too shallow. They targeted the compute die, the chip everyone could see. The compute die without this stack is an expensive piece of silicon with nowhere to put its data, and the controls on memory came as a follow-on, not as the original architecture of the restriction node. The high-bandwidth memory supply layer, the three-company concentration that provides stacked memory bonded directly against artificial intelligence accelerator dies. Status: choke point with no domestic bypass. China's accelerator ecosystem has no confirmed domestic high-bandwidth memory source at commercial volume or at the bandwidth specifications current workloads require. The dependency is structural, not incidental. The line does not stop at the memory supplier. Follow it forward into the node where the stack and the die actually meet. Advanced packaging: the process that integrates a high-bandwidth memory stack with a compute die requires an interposer, a silicon or glass substrate that sits between the two, routing the microbump connections between them. The connection density involved is extreme. Thousands of microbumps across an area smaller than a postage stamp, each one carrying signal. The dominant process for this integration is TSMC's chip-on-wafer on substrate packaging, the vehicle Nvidia uses to integrate high-bandwidth memory with its compute dies, per TSMC's own public disclosures and widely reported supply chain coverage. TSMC is in Taiwan, and it is inaccessible to Chinese customers under current restrictions. Think of advanced packaging as the junction box where every wire in a building terminates and connects. The wires themselves, the individual dies, can be excellent. But if the junction box cannot handle the connection density, cannot route signal cleanly between adjacent terminals, the wires never form a circuit. Chinese domestic packaging houses, including companies reports name as JCET and Tongfu Microelectronics, have documented advanced packaging capabilities and have received state investment toward expanding them. But industry analyst reports and trade press coverage suggest the microbump pitch and interposer complexity that high-bandwidth memory integration requires sits at or near the edge of confirmed domestic capability. No independent benchmark has confirmed domestic chip-on-wafer on substrate class yield at high-bandwidth memory integration specifications. The investment is real. The capability at that specific integration density is not independently confirmed. There is one meaningful difference between this node and the memory node it follows. The packaging gap is a process problem. With enough iteration, enough stacking cycles, enough yield learning accumulated domestically, it is the kind of node that can be reached without a single irreplaceable imported input. The substrate materials, the bonding equipment, the process steps, none of them depend on a monopoly the way the memory stack does. The next node, the line hits, is different in kind because it compounds a materials challenge with a process knowledge problem that does not reduce to any single tool or any single step. Node: advanced packaging, the interposer and microbump integration layer that bonds high-bandwidth memory to the compute die. Status: choke point. With a bypass under construction, not yet at volume. Domestic packaging investment is documented and state-supported. High-bandwidth memory class integration at the microbump density. The chip-on-wafer on substrate process requires is not confirmed at commercial yield domestically as of the most recent reporting period. The line from the packaging node runs toward the only plausible domestic entrant into the memory supply layer, Changshin Memory Technologies, known in the trade press as CXMT, China's primary domestic dynamic random access memory producer. Trace what CXMT has actually achieved. Chinese state media and the company's own announcements describe progress toward dynamic random access memory specifications approaching the DDR5 generation at commodity density. Independent fab-level verification of those specifications is not available, so those claims should be treated as company-reported. What the trade press and analyst community broadly agree on is this: CXMT has a functioning dynamic random access memory program and is approaching competitive specs at commodity density. That is a real achievement, and it matters for the map. What it does not do is close the gap to high bandwidth memory, making commodity dynamic random access memory and making high bandwidth memory share a starting material the way a bicycle and a carbon fiber aircraft wing both start from raw stock. The starting point is not the constraint. The constraint is the sequence of process steps between the raw material and the finished form. High bandwidth memory requires thinning each die to sub-100 micron thickness without introducing the micro cracks that kill yield. It requires drilling through silicon vias vertically through each thinned die, a process with its own failure mode library. It requires bonding 8 of those thinned, drilled dies in sequence so that a defect rate that is acceptable at the individual die level compounds across the stack and becomes a rate that kills finished product at a meaningful fraction of output. SK Hynix has been producing commercial high bandwidth memory since the first generation of the product. Samsung and Micron have followed. Each generation's failed stacks trained the next generation's process adjustments. CXMT has a domestic high-bandwidth memory development program, per reports. It has no confirmed commercial high-bandwidth memory product at volume as of the most recent reporting period. That gap is not a specification gap. It is a process recipe gap. Node, CXMT. As domestic high-bandwidth memory entrant, the line China needs to route from commodity dynamic random access memory into stacked high-bandwidth memory production. Status, choke point. With a bypass under construction, not yet at volume. A domestic dynamic random access memory foundation exists. The high-bandwidth memory-specific process stack, wafer thinning, through silicon via formation, and stacking yield is a reported development target with no confirmed commercial output at high-bandwidth memory class specifications. Here is where I want to push back on the bullish case directly. The argument that CXMT closing the dynamic random access memory gap unlocks a domestic high-bandwidth memory path assumes those two problems are on the same continuum. My read is that they are not. High-bandwidth memory is not fast dynamic random access memory. It is a distinct manufacturing problem at every stage past the base die. Wafer thinning at high-bandwidth memory spec through silicon via formation at the via density stacking requires, and above all, the compounding yield across 8 dies bonded in sequence. These are each separate process challenges, and each one needs its own iteration cycle to accumulate the failure mode knowledge that drives yield improvement. CXMT, closing the commodity dynamic. Random access memory gap is a necessary condition for a domestic high-bandwidth memory program. It is not a sufficient one. The node the map cannot yet read is stacking yield as accumulated process knowledge. Not the dynamic random access memory die itself, not the through silicon via drill, not any single step. The yield that compounds across 8 thinned dies bonded in sequence, where a defect rate that is manageable at the individual die level becomes a product killing rate at the finished stack. A stack with 8 dies, each at a 95% individual yield, finishes at a stack yield below 2/3. Move the individual yield to 99%, and the stack yield reaches roughly 93. The mathematics of compounding defects is relentless, and the process knowledge that pushes individual die yield from 95 to 99 is not documented in any patent filing at a level of operational detail that transfers to a new entrant. It is in the failure mode library, the records of stacks that delaminated in the 3rd thermal cycle, the vias that opened under bonding pressure at a specific die thickness, the micro-bump voids that appeared when humidity in the bonding chamber exceeded a threshold no specification sheet listed. That library is built from failed stacks. SK Hynix has been accumulating it for years across multiple high-bandwidth memory generations. You cannot acquire the crossing count by procurement. You can only run the iterations. Consider a bridge engineer who has built the same crossing 30 times. She knows which soil conditions cause the eastern pier to shift in the third year, not because it is in a textbook, but because it happened, was corrected, and was written into the next design. The 30 crossings are the moat. The strongest version of the permanent case for this dead end is that the failure mode library is not transferable through any channel China currently has open, and that the learning cycle cannot be compressed simply by spending more money, because the iterations take calendar time, thermal cycles, and physical stacks run and failed and diagnosed. If that knowledge is genuinely non-transferable, then domestic high-bandwidth memory at competitive yield is a decade-scale problem, not a 5-year one. The strongest version of the bypass case is that yield learning is iteration, full stop. It is not mysterious. If CXMT runs enough stacking cycles with enough state funding to sustain the losses from failed stacks, the failure modes will surface and be corrected domestically. China has the state capacity to fund iterations that no private company could sustain through the losses they generate. And there are architectural alternatives that reduce the severity of the dependency even without matching the incumbent yield. Near memory compute designs, Compute Express link-attached memory pools, chiplet architectures that distribute the bandwidth requirement across a larger die area. Reports suggest Chinese artificial intelligence chip designers are actively exploring exactly these approaches. An architectural workaround does not close the node. It changes how much pressure the node carries. The dead end is real, but not absolute. High bandwidth memory at competitive yield is a genuine process knowledge moat that no single acquisition or investment can shortcut. The architectural alternatives mean the dependency is not binary. The honest map call is this: high bandwidth memory yield is the hardest node on this map, and the timeline for routing around it is the most genuinely uncertain variable in China's artificial intelligence infrastructure build-out. Lay out what the map shows when read complete. On the bypass side, chip design tooling, the electronic design automation software, has seen partial domestic routing underway, with Chinese tools making documented progress even if the gap to the leading Western software is not fully closed. Mature node fabrication has meaningful domestic capacity at legacy process nodes, with SMIC and others producing at nodes that cover a wide range of applications below the most advanced geometries. Artificial intelligence chip architecture and instruction set design have both been demonstrated by Huawei, Micron, and others with functional products. The compute layer has been partially routed around. On the remaining choke point side, high bandwidth memory at commercial volume and competitive yield has no confirmed domestic source. Advanced packaging at the micro bump density high bandwidth memory integration requires is under construction but not at volume. Extreme ultraviolet lithography for next-generation dynamic random access memory scaling remains inaccessible. The network has routed around the nodes everyone was watching. It ran directly into a node that was not on the primary watch list. The hypothesis I am testing as I trace this map is the one that matters most for the forward read. The memory node is more durable as a choke point than extreme ultraviolet lithography, because the barrier is not one tool or one license. It is accumulated process knowledge, stacking yield, and supply chain depth distributed across years of failed and corrected stacks. If that holds, then the memory node outlasts the compute layer restrictions as the governing constraint on China's artificial intelligence build-out. The network is not self-contained. The gap is specific, and it sits one component over from where the controls were aimed. That high-bandwidth memory stack, 8 thinned dies, through silicon vias, thousands of micro bumps against the interposer, is still coming from Seoul and Boise. The accelerator board it bonds to may be designed in Shenzhen, fabbed in Shanghai, packaged domestically with increasing capability. But the object that makes it an accelerator rather than a compute die on a board is still imported. The map redraws when that changes. Until it does, one line ends at a node outside the border and the whole web routes through it. The question was never whether China could build a chip. It was whether it could feed one. And the answer, right now, is not entirely. And the gap is smaller than the headlines said, and larger than the trade press noticed, and it sits in a component that weighs less than a gram. Which node closes first? Domestic high bandwidth memory at commercial yield, or an architectural workaround that reduces how much high bandwidth memory the accelerator needs in the first place? And when either happens, what does it do to the rest of the map? Put your call in the comments. I will read the ones that disagree with me most directly. If you want to follow the map as it redraws, segment by segment and node by node, subscribe and turn on notifications. The next line we trace is already being built.